Definition of the adjoint of a matrix. Welcome, everyone. Today, we are going to dive into a very important concept in linear algebra, the definition of the adjoint of a matrix. Now, when we are working specifically with square matrices, you will frequently encounter a fundamental tool known as the adjoint, which you might also hear referred to as the adjugate. It is a vital concept to master because it plays a critical role in more advanced operations, such as finding the inverse of a matrix and solving complex systems of linear equations. Over the next few slides, I will guide you through the conceptual logic and the step-by-step procedure required to calculate it. Conceptual understanding. Now that we know why the adjoint is such a powerful tool in linear algebra, let's look at what it actually is. By definition, the adjoint of a square matrix, let's call it A, is simply the transpose of the cofactor matrix. Now, I know that sounds a bit technical, so to really grasp this concept, we need to look at its fundamental building blocks, minors and cofactors. We are going to dive deep into those in just a moment. If these terms feel a bit abstract or intimidating right now, don't worry. You can think of the entire process of finding an adjoint as a systematic transformation. Imagine you are taking your original matrix and replacing every single element with a new value, a value that represents the influence or the impact that all the other elements in the matrix have on that specific position. In the next few slides, I will show you exactly how to perform this transformation step by step. Step-by-step process to find the adjoint. Now that we have a conceptual grasp of what the adjoint represents, let's look at the practical application. Finding the adjoint of a matrix A of order n by n involves a specific four-step sequence. It might look a bit daunting at first, but if you follow the steps in order, it becomes quite manageable. So let us break it down step by step. Step 1. Calculate the minors. Now that we have an overview of the four-step sequence, let's dive into the very first step, calculating the minors. This is the foundation for everything else we are about to do. To find a minor, you look at every individual element in your matrix, which we denote as a sub-I, j for each of these elements. You are going to perform a specific operation. You temporarily cross out, or delete, the entire ith row and the jth column that the element belongs to. Once those are gone, you'll be left with a smaller matrix. The determinant of this remaining smaller matrix is what we call the minor, represented by m sub I, j. It might seem like a lot of work initially, but mastering this step is crucial before we move on to applying signs to create cofactors in the next slide. Step 2. Calculate the cofactors. Now that we have a clear idea of how to find the minors from the previous step, let's move on to step 2, which is calculating the cofactors. You can think of a cofactor as being essentially the same as the minor we just calculated, but with one extra layer, a specific sign attached to it. To determine whether a value stays the same or flips its sign, we look at the position of the element within the matrix. Mathematically, we express this using the formula C sub I, j equals -1 raised to the power of the sum of I and j, all multiplied by the minor, m sub I j. I know that formula might look a bit intimidating at first glance, so let me give you a much simpler way to remember it, especially when you are working with a 3x3 matrix. You can use what we call the checkerboard pattern. Imagine a grid of alternating plus and minus signs, starting with a plus in the top left corner, then a minus, then a plus, and so on, just like a checkerboard. This pattern tells you exactly which elements will keep their sign and which ones will need to be multiplied by -1. Keep this pattern in mind, because in the next step, we will use these signed values to construct our cofactor matrix. Step 3. Construct the cofactor matrix. Now that we have successfully calculated the cofactors for every individual element in our original matrix A, we need to organize them. Instead of leaving them as a list of separate values, we are going to arrange them into a brand new matrix. This specific arrangement is known as the cofactor matrix, and we denote it with the capital letter C. To visualize this, imagine placing each cofactor into its corresponding position from the original matrix. So, the first row of our new matrix C will consist of the cofactor from row 1, column 1, followed by the cofactor from row 1, column 2, and so on. The second row will start with the cofactor from row 2, column 1, and this pattern continues until we have a complete matrix of cofactors. Step 4. Transpose the cofactor matrix. Now that we have successfully constructed our cofactor matrix, we move on to the final step of the process. To find the adjoint, we need to find the transpose of that cofactor matrix we just built. As you might remember from our previous lessons on matrix operations, finding the transpose is quite straightforward. You simply obtain it by swapping the rows with the columns. In other words, the first row becomes the first column, the second row becomes the second column, and so on. Once this swap is complete, the resulting matrix is officially what we call the adjoint of A, which we denote as Aj. Mathematically, we express this relationship as Aj equals C transpose. This completes our transformation and gives us the final adjoint matrix. Detailed example. Now that we have walked through the theoretical steps and understood the logic behind finding the adjoint, let's put everything we've learned into practice with a concrete example. We are going to find the adjoint of the following 3x3 matrix, which we will call matrix A. This matrix consists of the first row, 1, 2, and 3, the second row, 0, 1, and 4, and the third row, 5, 6, and 0. Keep this matrix in mind, as in the next few slides, we will perform the step-by-step calculations for the minors, the cofactors, and finally, the transpose to reach our result. Step 1 and 2. Finding the cofactors, $. Now that we have our original matrix A, let's roll up our sleeves and get into the heavy lifting. On this slide, we are performing steps 1 and 2 simultaneously, calculating the cofactors. As we discussed in the previous slides, to find each cofactor, we first find the minor, which is the determinant of the remaining elements, and then apply the appropriate sign from our checkerboard pattern, using the formula -1 raised to the power of I plus j. Let's walk through the calculations for the first row. For the element in the first row, first column, we call this C11. We take the determinant of the 2x2 matrix with 1, 4, 6, and 0. That gives us 0 minus 24, which results in -24. Moving to the second element, C12, remember our checkerboard pattern tells us this one gets a negative sign. We find the determinant of the matrix with 0, 4, 5, and 0. This gives us -0 minus -20, which simplifies to +20. For the third element, C13, we use a plus sign. We calculate the determinant of 0, 1, 5, and 6, which is 0 minus 5, giving us -5. Now let's move to the second row. For C21, we apply a negative sign to the determinant of 2, 3, 6, and 0. That is -0 minus -18, which leaves us with +18. Next is C22. This position is a plus sign. We find the determinant of 1, 3, 5, and 0, which is 1 times 0 minus 3 times 5, resulting in -15. For C23, we use a negative sign. We calculate the determinant of 1, 2, 5, and 6. That is 1 times 6 minus 2 times 5, which is 6 minus 10, giving us +4. Finally, let's complete the third row. For C31, we use a plus sign. We find the determinant of 2, 3, 1, and 4, which is 8 minus 3, resulting in 5. For C32, we apply a negative sign to the determinant of 1, 3, 0, and 4. This is -1 times 4 minus 3 times 0, which simplifies to -4. Lastly, for C33, we use a plus sign. We calculate the determinant of 1, 2, 0, and 1, which is 1 minus 0, giving us 1. Once we have all these individual values, we will be ready for the next step, assembling them into our new matrix. Step 3. Form the cofactor matrix C. So our cofactor matrix, which we denote as capital C, is a 3x3 matrix where the first row consists of -24, 20, and -5. The second row contains 18, -15, and 4, and the final row is composed of 5, -4, and 1. Now that we have calculated all 9 individual cofactors in the previous step, we move to step 3, constructing the cofactor matrix. To do this, we simply take those values we just found and arrange them into a new matrix, maintaining their original positions. Keep this matrix handy, because in the very next step, we will perform the final transformation to reach our goal. Step 4. Transpose the cofactor matrix to get a J. Now, we have reached the final step of our process. In the previous slide, we successfully constructed our cofactor matrix, which we labeled as matrix C. However, remember that the cofactor matrix itself is not yet the adjoint. To finish the job, we must perform the fourth and final step. We swap the rows and columns of matrix. See, this operation is known as finding the transpose. If you look at the screen, you can see this transformation in action. We take the first row of our cofactor matrix and turn it into the first column of our new matrix. Then, we take the second row and make it the second column, and finally, the third row becomes the third column. As a result, we arrive at our final answer. The adjoint of A, which we denote as a J, equals C transpose, which is the matrix starting with -24, 18, 5 in the first row, 20, -15, -4 in the second row, and -5, 4, 1 in the third row. We have now officially completed the calculation. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. As you've seen in our step-by-step example, finding an adjoint is a multi-stage process, and it is very easy to trip up along the way. First, the most frequent mistake I see is forgetting the transpose. It is very tempting to finish calculating all those cofactors, arrange them into a matrix, and think, done, I've found the adjoint. But remember, the cofactor matrix is not the same thing as the adjoint. You must perform that final step of swapping your rows and columns to get the transpose. If you skip this, your final answer will be incorrect. Second, watch out for sign errors. When we were calculating the cofactors in the previous slides, we used the formula -1 to the power of I plus j. It is incredibly easy to lose track of that negative sign. To prevent this, I highly recommend you always double-check your work against the checkerboard sign pattern we discussed earlier, the one that alternates between plus and minus. Finally, be mindful of simple arithmetic slips. As we just demonstrated in the detailed example, finding an adjoint requires a long sequence of small determinant calculations. Because every single element in your final matrix depends on these individual calculations, a single mistake in just one minor can cause a domino effect, making your entire adjoint matrix incorrect. Take your time and be meticulous with your calculations. Key takeaways. First and foremost, remember the core definition. The adjoint of a square matrix A is simply the transpose of its cofactor matrix. If you can remember that relationship, you've mastered the concept. To avoid the common mistakes we discussed in the previous slide, always follow the strict, step-by-step sequence we practiced. You start by calculating the minors, then move to the cofactors, arrange those into the cofactor matrix, perform the transpose, and finally, you arrive at the adjoint. If you skip even one of these steps, especially that final transpose, your result will be incorrect. In terms of mathematical notation, you will see it written as Edge A equals the transpose of the matrix of cofactors, where C sub I, J is the cofactor at row I and column J. Lastly, keep in mind why we are learning this in the first place. The adjoint is a vital prerequisite for calculating the inverse of a matrix. You will use it in the formula where an inverse equals 1 divided by the determinant of A, multiplied by the adjoint of A. All right, we have reached the end of our lesson, so let's wrap everything up with the key takeaways to ensure you have a solid grasp of the concept. Make sure you practice these steps with a few more examples, and you'll find that this process becomes second nature. Well done today.